We are in a new section. This is a nice Stardew Valley shirt celebrating a gift from my friend. We're going to talk about exponential functions. Okay, so this whole chapter talks about exponential functions, things that grow exponentially or decay exponentially, logarithmic functions. That's really exciting. And people get scared with logarithms, but we're not going to do anything too scary in this class. And some of the applications that we can do so that we're really prepared for chapter 6 is when we get into more finance stuff like loans and annuities and interest. We do a little interest here, but most of that's going to be in chapter 6. So I'm excited for where we're going in this class. Hopefully you are too. So we'll start by saying what's an exponential function, and I'm going to give you a little example to start, a motivating example. Maybe you've heard it before. Well, let's say you have a piece of paper, piece of regular paper. Maybe it's about 0.1 millimeters. Turns out 0.1 millimeters is about 0.0000006 miles. Okay, so this is a small fraction of a mile. And every time we fold this piece of paper, every time we fold it, it gets twice as thick. If I fold it once, twice as thick. Fold it twice. Now it's 4 times as thick as it used to be. Fold it a third time. Now it's 8 times as thick as it used to be. Fold it a fourth time. Now it's 16 times as thick as it used to be. Every time it keeps doubling in thickness. So the question is, how many times do I have to fold this piece of paper until it reaches the moon, which is like 290,000 miles or something? Something like that. I don't remember. That's an exponential function. Every time we fold it, it's getting twice as thick. You might say, Jason, you're never going to be able to fold a piece of paper and get it to the moon. Well, let's look at that. So let's go into Desmos real quick. Turns out we can model this function with an exponential function. I'll tell you more about where this comes from later, but it's 0.0000006 times 2 to the x. So you can see, it's not very many miles thick for a while. And then, whoa! If we fold it 25 times, if I only folded it like 4, but if we folded it 25 times, it'd be 2 miles high. It'd be 2 miles thick. You're never going to do it. The record is like 12 times or something, and I don't think that's a standard sheet of paper. And then, oh my goodness, you fold it 30 times, 51 miles thick. Oh my gosh, it's getting huge. Zoom out, we need like 280,000. So let's zoom out a little faster. All right, 280,000, put that for my Y coordinate. When are we at 280,000 miles? We only have to fold it about 42 times. You fold this 42 times, it's gonna get to the moon. Right? Anyone wants to go to the moon? Just start folding some paper. You can get it to 42 times. It'll reach it there. All right. So that's one application, a silly application of an exponential function. Exponential and functions are all about things that increase by a specific percentage rate. So it's not like linear. Linear was like, oh, let's increase by 100 every time. But here, it's let's increase by double every time. So instead of adding the same thing every time, that's linear. We're multiplying or dividing by the same thing every time. That's exponential. So that's the difference between linear and exponential. And of course, it has that very steep graph. You can tell here, by the way, graphs of exponential functions are sometimes hard to picture because way over here, it looks like very horizontal. Way over here, it looks very vertical. That's something tied to something really cool called log scales. That's a great way of graphing some things like this, which can ordinarily be kind of hard to visualize. So that's what we're going to here. Our answer is 42. Don't worry about where that comes from. That's like 5.3 stuff. But this is a good motivating example. So let's formalize this a little bit. An exponential function is a function that grows or shrinks at a constant percent rate. So maybe it doubles every hour. maybe it decays by a third or 30% every day. These are all examples of exponential functions. And they can be written in two forms. Well, a lot more than two forms, but these are the two forms that we'll talk about. An a times 1 plus r, or an a times b to the x. And as a quick warning, this is not the same thing as a times b to the x here. Only the b has the exponent. Okay, so a times b to the x is what we have. The exponent is only attached to the b. So what do all these letters mean? Oh, lots of definitions here. A is the starting value. So when I made my graph, look, it is a times b to the x. A is that starting value. This is how many miles thick our piece of paper is starting out to be. Not very many miles. Okay, R is the percent growth or decay rate written as a decimal. So what was our R value? We were doubling. Doubling is growing by 100%, which sounds a little weird, right? If I'm at 50 and I grow by 100%, that's growing by another 50. That is doubling, right? If you're at 50 and you add another 50, you're at 100 now. You've doubled. So that was our R value was 100%, which was 1. So what we had in ours, right, was A, which was at, 0.0000006 times 1 plus R, which was 100% or 1. Well, 1 plus 1 is 2. So you can really see that, okay, we did have the same thing. But remember, there's two forms that we can use. The other one uses the B value. The B is the growth or decay factor or multiplier. So if it tripled every day, that would be a B value of 3. It would be an R value of 2. Growing by 200% is tripling. So B and R can be a little confusing to keep them straight. So we were doubling every time we folded, so our B value was 2. The domain of an exponential function. Domain's all the inputs. What input can you put in here? Yeah. Any input to the left. What about to the right? It's going to grow really fast, but yeah, there's no asymptote here. We can input anything we want. So the domain for really any exponential function is all real numbers. Negative infinity up to positive infinity. We can plug anything we want into exponential functions. If something's in this form, though, the range is going to be a little different. And again, we're not actually hitting 0 here. It's just really close to 0. Let's look at a different exponential function. Right? If we look at a more normal exponential function, it gets really close to 0, but it's never actually going to equal 0. So the range is going to be not quite 0. 0 is not included, but the output can get as big as we want. Remember, domain is all the inputs that make sense. Range is all the outputs that make sense. Let's get some practice. India is the second most populous country in the world with a population, I think China is the most, population in 2023 of about 1.4 billion people. Population's growing by about 0.8% every year. Write an exponential function for India's population. Okay, so which form makes more sense for us to look at here? Either work. But should we look at the form with R or the form with B? Which one does this look more similar to? To me, it looks more similar to the R form because it tells us it's growing by a certain percent. So if we can convert that percent into a decimal, that gives us our R value. So 0.8% converted to a decimal. Just move the decimal place over twice. That's 0.008. 0.8% is not quite a percent, and a percent is 1 out of 100. So that's our R value. What's our A value? A is the starting value. What's our starting value here? 1.408 billion. So when we use this A and this R and use this function over here, we do have to say the units. F of x is a times 1 plus r to the x. We use that form. A is 1.408. R is 0.008. We can simplify inside the parentheses. Say that our function is 1.408 times 1.008 to the x. And we have to say what these units are. So x is years after 2023. It's not the year. It's how many years after 2023 we are. Otherwise, our starting value will look very, very different. And f of x is India's population in billions. That's going to be our answer here. How do we predict India's population in 2025? We are not going to plug in 2025. Okay, that'll say in 2025 years from now, what will their population be? There's a lot of things that you could say about that. Who knows what the world will look like in 2,000 years? But we're going to just plug in x equals 2. Why? Because x is how many years after 2023 we are. So this is 2 years after 2023. So just find f of 2. That'll be 1.408 times 1.008 to the second power. And we're going to get that our answer is 1.408, 1.008 squared, about 1.431. I'm going to use the same number of significant figures as what we originally started with, or about 1.431 billion people in 2 years. All right, so it doesn't look very different, but that is still 30 million or 23 million new people in 2 years. That's like 10% of the United States population. Anyway, that's how we can do it. Let me know if you have questions about this, and good luck.